Hi, good day. My name is William T. Dongo. I'm here today to give a lecture again about climate control and refrigeration technology. It's residential and commercial air conditioning. The lesson topic we're going to be talking about is lesson number 3. That's system components, mechanical and mechanical diagram. We'll be talking about the 4 major components. We got the compressor, the condenser, the metering device, the evaporator. You got the condenser, fan motor, and the evaporator fan motors too. Okay? So, this is the next subtopic that we'll be talking about. Okay, now system components and mechanical diagram. The 4 major components are the beginning of the refrigeration cycle. That's the compressor. We'll have a discharge gas outlet and a suction vapor inlet, which is the suction line. It will pump refrigerant vapor in only one direction. Discharge outlet will be hot. Suction vapor inlet will be cold. Okay, we talk about the compressor design. Just like I showed the picture on the other lesson, you got the compressor. Okay. Compressor design. Compressor design, typically there is 2 compressor design used in residential and light commercial air conditioning. They are the reciprocating and the scroll type. The reciprocating compressor may be fully hermetic or semi-hermetic. Fully hermetic compressor most common in modern residential system. Modern residential system is plus lubrication system, suction gas cool, welded shut, could be serviced without cutting it open. No access. Usually throw away unless manufacturers need it for examination or warranty. Capacity could range up to, but not too limited to 30 tons. And then we have a semi-hermetic. Are open use in largest system found in commercial application. Bolted together at locations conducive to service and repair. Can be made of cast iron, heavier than fully hermetic. Pressure lubricated system. Open the air cooled by using extended surface area like the ribs around the casing. Okay. These compressors are positive displacement and use R12 or R22. All compressor must have some type of cooling means. Discharge line leaving the compressor should not exceed 225 degrees Fahrenheit. Hermetic compressor all have rubber mounting feet. In air conditioning, the compressor is usually located outside the condenser. The scroll compressor is a new type of compressor. It has a spiral shaped form. One spiral is stationary. The second orbits within. Special pockets of suction gas form, and these pockets are squeezed towards the center to form discharge gas. The compressor provides high efficiency. It has no valve Therefore, there is no valve compressor loss. Suction and discharge are separated and reduces heat transfer. There is no clearance volume providing the expansion gas. Okay? And then liquid slugging will not harm compressor. Scroll compressor size vary from 18,000 BTU up to 39,700 BTU, which can be replaced. Reciprocating compressor that range in capacity from 16,500 BTU up to 43,000 BTU. 412,000 BTU is equal to 1 ton of AC. It also doesn't have the need for accumulator or start kits. Compressor can start under any load. Compressor thus required to operate in one specific direction. If power is interrupted briefly, compressor will run in reverse, operate noisily, cause internal overload to rip, suction pressure will rise, discharge pressure will fail, amp draw will be 50% of rate amps draw. To prevent reverse rotation, a 2-minute time delay relay should be installed. Okay, now we talk about the purpose of the compressor. The purpose of the compressor, it is considered to be the heart of the system. In simplest terms, it is a vapor pump. It increases the pressure in the system from the suction pressure level to a discharge pressure level, circulating refrigerant throughout the system. Okay, now that's conclude about the compressor. Now we're gonna talk about the condenser. The condenser design. The coil are copper or aluminum with aluminum pins to add to the heat exchange surface area. Some equipment use the bottom pin rows for a subcooling circuit. It is common for liquid line to be 10 degrees to 15 degrees cooler than the condensing temperature. High efficiency condenser are 15 degrees plus subcooler. Most air conditioning condenser are cooled by forced air. Condenser cabinet is usually located to outside. Okay, weatherproofing is a must. Most small equipment is assembled with self-tapping sheet metal screw. Side air discharge condensing unit discharge air out of its side. Fan and motor are protected under top part of cabinet. Any noise generated will be discharged with the leaving air. Top air discharge, condenser discharge air out of the top of the unit. Air and noise are discharged out of top of unit. Again, that's a discharge is rain, snow, and leaves can fall directly into the unit. Fan motor can be protected with rain shield. Fan motor bearing are in vertical position, so the end bearing needs a thrust surface. And then you need a good lubrication for the bearing. And then the purpose of the condenser. So that means the condenser purpose is to reject the heat that was picked up by the evaporator. The heat is in the form of heat-laden hot gas. Hot gas is to condense to have the greatest amount of BTU removed. Subcooling refrigerant below the saturated temperature. The lower the temperature in the liquid line, the greater the system heat removal capacity. This results in a more efficient system. Okay, just like this one right here, I got a small picture of the diagram here. Okay, you got here a diagram here, you got the condensing unit right here. Okay, then you have your evaporator inside there. This is a split unit. This is located outside the house. And then the same thing as this one. Okay, and then here we got here is the cycle here. Okay, same thing at the bottom here. Then we got here is the scroll. This is the theory of the scroll that's inside the compressor, and then this is the picture of the compressor itself. And then you got this one right here. Okay, and then we got one here, your TXB, your thermostatic expansion valve. The same thing as this one. Okay, and so what's this two diagram here? Thermostatic expansion valve. Then you get this one too. Then over here is your okay. So I'm gonna continue on with what I'm reading. Then we're gonna go to the metering device design. I show you a metering device there. So the thermostatic expansion valve and the fixed bore metering device, either capillary tube or an orifice, are type most commonly used in air conditioning. The TXB follows the same characteristics as the valve used in refrigeration, with the exception of its being in a high temperature range application. TXB are more efficient than bore devices. It allows the evaporator to reach peak performance faster. It allows more refrigerant into the evaporator coil during a not a pull down. Okay, not a pull down. TXB do not let refrigerant pressure equalize during the off cycle unless the valve is made to equalize them. The compressor must have a start capacitor. Some manufacturers have a bleed ports on the valve to allow equalization of pressure. Capillary tube and orifice devices allow equalization, therefore low starting torque motor can be used. A TXB has several components. We have the valve body, an accurate machine piece of solid brass, or stainless steel. Holds the rest of the components and fasten the valve to the refrigerant piping. Several different configurations. Most valves have an inlet screen. The valve diaphragm, made of thin metal, sits under the round dome-like top of valves, moves the needle and sits in response to system load changes. Okay, and then the needle and the seat control the flow of refrigerant through valve, made from stainless steel. Okay, and then we have the spring. The spring, it overcomes the diaphragm to close the valve by pushing the needle into the seat. One of the three forces that act on the diaphragm. Okay, tension is factory set for a predetermined superheat of 8 degrees to 12 degrees. And then we have the sensing valve. Detects the temperature and converts it to PSI to act on diaphragm. Second force to act on the diaphragm, opposing the spring. And the third force, that's the evaporator PSI. The capillary tube is a copper tube with a very small calibrated inside diameter. And then you have the PIX orifice. PIX orifice, brass body that has an actuator placed inside. The actuator is the PIX bore. Different sizes are available and are interchangeable according to application. Allows equalization of pressure. It has to be installed in the proper direction to prevent discrepancies in refrigerant pressure. Now, the purpose of the metering device. Metering device is responsible for metering the correct amount of refrigerant to the evaporator. Restricts the liquid entering and lowering the pressure. 29% of refrigerant passes as it goes through restriction. There is 25% vapor and 75% liquid mixture at beginning of evaporator at the lower pressure. Temperature and pressure relationships of refrigerant use to find out boiling point. 25% vapor is now absorbing heat, causing the 75% liquid to begin vaporizing because of heat being absorbed. The last part of the evaporator is where the refrigerant is now superheated after this all saturated. The superheat vapor now leaves the evaporator to enter the compressor to continue the cycle. And then it will go to the evaporator cycle now. The evaporator design. The evaporator is the components that absorb the heat. It is made usually of copper or aluminum tubing. It has aluminum pins attached to the coil to give it more surface area for better heat transfer. Several different designs for airflow through coil and drainage of condensed water. The different designs are the A coil, used for up flow, down flow, and the horizontal flow. Two coils with their circuit side by side and spread apart at the bottom. Condensate pan at the bottom of A pattern. The horizontal flow drain pan placed on the bottom of coil with coil on its side. It is not recommended for airflow to go through the coil in series A. And then you got the slant coil. Slant coil can be used for upflow, downflow, and horizontal flow. A one-piece coil mounted at an angle, usually 60 degrees. Condensate pan located at the bottom of the slant. When a coil circuit in an evaporator becomes too long and causes excessive pressure drops, a distributor can be used to split the coil circuits and distribute refrigerant evenly. Okay. Now the purpose on an evaporator. Purpose of evaporator: immediately after metering device, the vapor from the mixture will be absorbing the heat. Mixture enters the evaporator. Time metering device outlet is the evaporator inlet. Evaporator outlet is cool. The boiling temperature of the liquid refrigerant determines the coil operating temperature, usually about 40 degrees Fahrenheit. Its operating temperature is considered high temperature refrigeration. The evaporator is a heat exchanger that transfers heat from room air to the refrigerant. Two kinds of heat must be transferred. You have the sensible heat, that's lower the air temperature, and then you have the latent heat. Change the water vapor in the air to condensate. The evaporator coil boiling temperature usually operates at 40 degrees Fahrenheit, that's 68.5 psig, with a return air of 75 degrees Fahrenheit and a humidity of 50%. Typically, airflow temperature across the evaporator coil is 20 different degrees difference, also known as the split. With high humidity, it can get as low as 12 degrees difference. Okay, the density of the designer of the evaporator design condition. The designer or engineer must be familiar with local design practices. The airflow across the same coil installed in two different locations of the country will accomplish different air conditions. The evaporator may come in the enclosed cabinet. Okay, cabinet should be insulated to prevent sweating on the outside. Built into the air handler. Okay, and then we talk about the other components. The other components that we will be using the air conditioning is the condenser fan motor. Condenser fan motors turn the fan directly, or fan may be belt driven to remove the heat out of the condenser. Usually a propeller type. Length and pitch of blade affects the amount of air being removed properly. And then the amount of blades could affect, the amount of blades could also affect the amount of air, okay, or heat to be removed. Evaporator fan motor turns blower fan directly or can be belt driven. usually squirrel cage blower type. And then the other one here, components arrangement. The arrangement of the components. You got the evaporator and the metering device, usually located together. The compressor and the condenser, usually located together. Optional equipment. Optional equipment can cost different components and piping, configuration, and arrangement. Arrangement of these components should not affect the refrigerant cycle if properly designed. Now we talk about, go back to the different parts of the refrigeration cycle. Okay, let's summarize it. The refrigeration cycle, we got the compressor, discharge the refrigerant to the condenser. High pressure, high temperature vapor. And then it goes to the condenser. The condenser releases heat from the refrigerant. Refrigerant changes from high pressure, high temperature vapor to high pressure, high temperature liquid. And then we go to the metering device. Metering device drop the pressure of the refrigerant. Changes high pressure, high temperature liquid to low pressure, low temperature liquid. And then again it goes back to the evaporator where the heat absorb heat. The heat from the conditioned space. Low pressure, low temperature liquid change to low pressure, low temperature vapor by absorbing this heat. Return to the compressor in vapor state and starts all over again. Just like that one is just the one I explained on the basic refrigeration cycle. Okay, that's the end of this lecture. And then over here you learn the different components, the advanced part of that. And then I thank you very much. And then again, every time I come in, I said, "You're professor today." For today, my title of myself to this lecture is Chief Machinist Mate Surface Warper William T. Dongo, U.S. Navy retired. Okay, for this lecture, because I'm a retired Navy, and in the Navy I was a good training chief petty officer. I used to run a auxiliary division, machinist mate power plant, and I have trained so many people that they become very, very good technician when they get out of the United States Navy. For me, I stayed 20 years and I retired as a machinist mate, chief petty officer, Surface Warper William T. Dongo. And I'm a U.S. disabled veterans too. So I thank you. This one is just for training purposes, and thank you very much.